In this video, we're going to examine more properties about the t-test and in hypothesis testing in general. With the hypothesis testing framework, we make inferences to population parameters based on sample data. And this is stated in the hypothesis. We make a conclusion regarding those hypotheses. One of the conclusions we potentially would make is that we reject the null hypothesis. We would claim in that instance that there is sufficient evidence for a difference in population means, and that's based on the sample data. The second conclusion that could potentially be arrived at is that we do not reject the null hypothesis. I will abbreviate, indicating that there is not enough or insufficient evidence based on the sample data that the population means are different. Recall the criteria that allow for these conclusions to be made. A rejection of the null hypothesis may be concluded when the p-value is sufficiently small, usually less than or equal to alpha, which typically is 0.05. That's the one I remember because a non-rejection is when the p-value exceeds alpha. Because sample data is subject to sampling variability and thus sampling error, it is absolutely possible that the conclusion we make is not accurate with what's going on in the population. It may be that the sample was inconsistent with what's truly happening in the population. So I'm going to make a little table that hopefully organizes some of the possible outcomes when making a conclusion in terms of could that conclusion be incorrect, i.e. erroneous, or not. In this little table that I'm going to make, I'm going to have the column state the conclusion based on sample data. So those conclusions are either the data suggests a rejection of the null hypothesis, or that we do not reject the null hypothesis. The rows here are what I'm calling the truth. This is unknown to us, so that's what's going on in the population. We don't know really is whether the null hypothesis is true or if the alternative is true. We don't really know. What we do see is what is illustrated in sample data. So those are our options here. So there are 4 potential outcomes. 2 of these rectangles represent a correct outcome, and 2 of them represent an incorrect conclusion. Again, we don't ever know if an error is made. So let's look at one of the correct rectangles here. Let's suppose that your sample data was such that you got a small p-value, so you're going to reject the null hypothesis. Now, if we're rejecting the null hypothesis and it so happens to be that the alternative is true, then that would be a correct outcome. Rejecting the null while the alternative is true. Again, we don't know what the truth is, so this is theoretical. The other correct rectangle is over here. This is when the data suggests that we do not reject the null hypothesis. If we do not have evidence against the null, and the null hypothesis is true, then that would be a drive-in situation. So these other two rectangles are the errors. These are not cleverly named. This one is called a type 1 error, and this one is a type 2 error. One way to think about errors, reflect way back when we talked about probability with medical testing, sensitivity, specificity, true and false positives, true and false negatives. A type 1 error is akin to making a false positive, because that would be saying when we reject the null hypothesis, we're saying that there's a difference. But if that difference was wrong, that is like a false positive. That's like saying that the disease is present, there's some change, but it's not there. Therefore, this other error is akin to making a false negative. There are probabilities associated with these. And we're really just going to focus on type 1 error, because that's the one that we have control over. As a researcher making conclusions, that conclusion is based off of that p-value, and you're comparing that p-value to alpha. So there is a probability of alpha of making a type 1 error. Another important term that is thrown around is what's called the power of a test. And there's a probability associated with it. We're not going to dive deep into it, but the power of a test is the ability of that test, that sample data, to demonstrate that a difference exists when the difference actually exists. So the power of a test can be improved in certain ways. We won't get too deep into that, but that term will get thrown around, talking about the ability of a test to accurately identify when differences exist. Up until this point, we've often said that the default value for the level of significance is 0.05, and that's still true. But truly, the choice for alpha should be chosen based on the consequences of a type 1 error. And we're going to discuss some of those consequences here in a moment. Let's look at a particular example to put some of these errors into context. A diagnostic test for prostate cancer is the analysis of prostate-specific antigens. A 5 nanogram per liter level is suspect for early forms of cancer, and 8 nanograms per deciliter is used as an indicator that cancer is present. So let's consider a hypothesis for this scenario. Without any additional indication, one might suspect that you or any person is not possessing cancer. Person is cancer-free or healthy, but unless there's some evidence to suggest otherwise, then you might start to believe that you or this person has cancer. And I'm going to draw a image to help illustrate where these numbers are going to come into play. So this first curve, now I don't know if PSA levels are normally distributed. I'm just going to roll with it. But let's call this axis PSA. And this first curve that I've illustrated is going to represent the distribution of PSA levels for folks who do not have cancer. I'm going to draw a second curve to represent the folks and their PSA levels if they do have cancer. So this is the distribution of PSA levels for the folks with cancer. And I'm going to put a tick mark for 8 here and another one for 5 there. I'm going to put a vertical line here just so it's clear in my explanation to follow. So let's focus on the area under the curve for the cancer-free individuals. Let's consider the area beyond 8. This may not be drawn to scale, but there are certainly going to be some folks out there who have an inflated PSA level, but they may not have cancer. So this blue shaded area is representing the proportion or percentage of folks who do not have cancer. They have high PSA levels. So they are going to be misdiagnosed with cancer. So would that be a false positive or would that be a false negative? Well, that would be a false positive, right? Because they just have high PSA levels, but they don't have the cancer. Okay, let's consider the false negative region. This would be individuals who have cancer, but their PSA levels are low. So they were not alerted of concern based on this indicator for cancer. So that would be, I'm going to shade it in red, that would be these folks. Maybe even all the way up to 8. The red shaded region, those are the folks who do have cancer, but their PSA levels are low. So that's if you were able to find the area in those curves, those would be the false negatives. So this threshold for the false positives, that has been defined as such that is represented by alpha. That is the probability of a type 1 error. These are the folks who do not have cancer, but have been identified as having it, right? False positive. The folks represented in red, that proportion, there is a probability associated with it. We're not going to worry about it too much, but that would be the probability of a type 2 error. You can think in your own, what's worse in this context? A false negative worse? Is a false positive worse? Something to kind of grapple with. So something that we do in statistics is we have the ability to protect against a type 1 error. We are able to define alpha, the level of significance, which protects against type 1 errors. If you think about the consequence of a type 1 error, this is kind of what you want to think about. If the consequence is very severe, maybe more severe than a false negative, then you might want to make your alpha small, right? The default is 0.05, but we often also use 0.01 and 0.10. Those are all typical values. I want to go over briefly another example, one that is not uncommon in our daily lives. In our judicial system, recall that defendant is innocent until proven guilty, right? And the alternative hypothesis would be guilty. So that's the default, right? The innocence would be like the default basis, what they are testing against. And if sufficient evidence beyond a reasonable doubt is weighed against that, then that defendant would be claimed guilty. Let's consider the conclusions for this scenario when we reject or we do not reject the null hypothesis and the potential errors. If the data demonstrates beyond a reasonable doubt that we should reject the null hypothesis, then there is evidence that the defendant is guilty. However, a non-rejection does not prove someone's innocence. No. However, what do they say in the TV shows? They say they are not guilty. So there's not evidence for guilt, right? Not evidence for guilt. They don't prove anyone's innocence. They just can't prove their guilt. Let's consider now the type of errors that can arise here. So I'm going to try to squeeze this in. Possible error. This could be a possible type 1 error in which what's the consequence? If this was an erroneous verdict, then they are claiming that the individual is guilty, but they are not. So this would be an innocent person doing the time or whatever the punishment is. So this is an innocent, I'm going to say innocent person goes to jail. So that's no fun. What about the second conclusion? What is happening here? This is a possible type 2 error in which the consequence would be, okay, well, someone is found not guilty, but they actually are. In this case, I guess how you could describe it is a guilty person gets to walk free, right? So what's worse? Type 1, type 2? I can't answer that for you. That's based on your own perception. But in this more classic example, the guideline for establishing is there evidence for guilt or is there not evidence for guilt, that is guided by hopefully what they call beyond reasonable doubt, right? Here, alpha is like the reasonable doubt. I never really knew what that meant until I started teaching statistics and thought about this a lot more than maybe the typical individual. So that's all about errors. We're going to identify what types of errors could have been made in various conclusions. So see you there.